So I'm here to introduce our two faculty members. Karsten Heeger is the Eugene Higgins Professor of Physics, Director of the Yale Wright Laboratory, and co-director of the Yale Center for Invisible Universe. His research focuses on the study of neutrino oscillations, neutrino mass, and dark matter. Dr. Heeger was involved in the discovery of solar neutrino oscillation with the Sudbury Neutrino Observatory, also known as SNO, in Canada. This discovery led to the 2015 Nobel Prize in Physics. He was also involved in the first observation of reactor neutrino oscillations with CamLand in Japan. The underground laboratories of both these experiments are featured in the film you just saw. Dr. Heeger's work has been recognized with a number of awards, including the 2016 Breakthrough Prize in Fundamental Physics. He is also a Fellow of the American Physical Society. Dr. Heeger received his undergraduate degree in physics from Oxford University and his PhD from the University of Washington in Seattle. He was on the faculty at the University of Wisconsin before coming to Yale. In 2013, he was recruited to lead and direct the new Yale Wright Laboratory. In 2024, Drs. Heeger, Reina Maruyama, and Priya Natarajan co-founded the Yale Center for the Invisible Universe for the study of neutrinos, dark matter, and related science. Reina Maruyama is a professor of physics and astronomy at Yale, a member of Yale's Wright Lab, and co-director of the Yale Center for the Invisible Universe. She develops technologies and carries out experiments to probe the underlying physics of fundamental symmetries, origins of the universe, and nature of neutrinos and dark matter. Dr. Maruyama has been the principal investigator and spokesperson of 6 local and international experiments. She has received numerous awards, including being named a Fellow of the American Physical Society. Dr. Maruyama was a member of the IceCube experiment construction team at the South Pole, leading the deployment and testing teams from 2008 to 2011. The location of this experiment is also featured in the film. Dr. Maruyama received her Bachelor of Science degree in Applied Physics from Columbia University and her Master's and PhD in Physics from the University of Washington. Before joining the faculty at Yale University, she was on the faculty at the University of Wisconsin and a postdoctoral researcher at the University of California, Berkeley. In 2024, Dr. Maruyama co-founded the Yale Center for the Invisible Universe, along with Dr. Heeger and Dr. Priya Natarajan. So please give them a warm welcome.
Reina, it was really cool seeing your face for just a second in the film. I wanted to ask, in the IceCube deployment, there were 2 lasers. One was green, one was red. I'm assuming for calibration, but what were you guys calibrating for?
Yeah, hi Jack. That was a really fun deployment. So what you're seeing with that sequence with camera is so we actually deployed a camera to calibrate the ice, and different color, different wavelengths of light travels differently in the ice, and so we wanted to see, if there is a difference between the green and the red laser. It's kind of cool because you could see the ice freezing over time. So when you do that, so you shine the light out. You start out with water, and there's a boundary between water and the ice beyond it, and so there's like a reflection happening. And as the ice right around the dome is actually a little bit cloudier than the bulk ice, and so you can see like ice freezing over time, and you can see that. The other cool thing that we could see with that camera being deployed was first, we have to say goodbye to our to the instruments going down into the ice. And as the camera was being lowered, we could look out into the surrounding ice. So for those of you who don't know IceCube, maybe I should say a little bit, how the experiment works. So we take the Antarctic ice and we drill a hole about 50 centimeters in diameter using a hot water jet, 2.5 kilometers deep into the ice. And then we pull the drill out and we put these instrumentation in. And this camera was attached at the bottom of one of the strings, we call it, and then above it are 60 photon sensors. So so we lower this whole string of sensors in, and the camera is at the bottom. as the camera was going down, we could actually see out into the ice. You could see ash layers, which is layers of ash that settled onto the Antarctic ice over the history of Antarctic ice. So basically 100,000 years of history going right, it was like going down, passing right in front of our eyes as this camera was being lowered. So that was kind of fun. And so that was compared with data from people sending out light into the ice. And you could see these dust layers, and we could actually map out when volcanoes erupted in different places of the ice. So long answer to your question.
Hi, thank you for being here. I really love the film, and I'm curious, seeing this as a story and a cinematic masterpiece, I thought it was quite beautiful. It made me think about astronauts having the overview effect. When they go up to space, maybe they look and they see the Earth for the first time from space, and there may be a psychological shift or something happens, maybe not. And it's this kind of extreme moment of seeing something from a distance and then looking. Do either one of you, or have either one of you had that experience while watching this, kind of from a distance, and perhaps the visual language of the film? Was there a moment in the film that gave you the overview effect version in your own work looking at this?
Yeah, maybe I'll start and Reina should chime in. It was really interesting to first watch this and also hear what the director had in mind. So when we communicated with the director, he sent us the movie. He said, well, it was supposed to be meditative, contemplative, and so on. And then I was thinking back. I worked at all three sites, and what I remember from working there was busyness, the smell of fuels, the noise of the underground lab. So the day-to-day operation was really quite different than what you experienced in this movie. I mean, I have to say, yes, there are moments of awe when you think about actually what you do, that you built a detector 6,800 feet underground, and you can look at solar neutrinos. That is quite remarkable. Or when you stand at the South Pole and you look out and you see all these science experiments. But it takes really that moment of stepping back and thinking about the bigger picture, that you then perhaps have this feeling and this emotion of awe. I think one site or a couple of sites that are quite remarkable is, for example, when you look inside the Super Kamioka detector, it's just a massive cavity. These arrays of photomultipliers, the reflection from the water, that is just a scale that you usually don't see, and that can be really quite a sight. But I remember when I started out as a graduate student, we built the snow experiment. It was day after day, going with the cage 2 kilometers underground with the miners and walking in the drift and changing into clean room suits, and there was not necessarily much awe. It was it was a grind. It was a grind building the experiment and having very long days, 12 and 14 hours underground, and not knowing if the experiment would actually work. And so it's now in hindsight that you step back and have this feeling. Yes, that was actually quite remarkable.
Yeah, I agree with that. There's definitely so the looking from above view. So the view that they showed in the film, where you could see the detector and like the tunnels in the mine. So I think those are artist renditions. So we don't ever see that. It was kind of cool to see artist rendition of IceCube with like all the photosensors floating in the ice. So that was pretty cool. To just imagine like what neutrinos must be seeing, as they go through the detector. But I think it's a lot busier. It's a lot more people. I think I remember like a lot of the preparation that went into to get there. So to go to the South Pole, to build things at the South Pole, you really have to have everything with you. And so, we talked about building these as if they were, space mission kind of things, because we deploy these instruments and we never see them again. We tested all of these photon sensors beforehand. So all the preparation that goes into building these things is what I remember. I remember the people. You go there, you build all of these things together. I led teams of students to test all the optical modules that you saw. The ones that you saw, I remember those names well because those are the ones that didn't work. They got left behind. So Hungry Hippo was like, it was like a troublemaker. I remember that really well. And then teams of people who made it work. So you get there, the ice drillers who told me you better show up on time or else, they really helped us make this experiment work, and then all the other fellow scientists. Everybody's there on a mission. You're all there for the same goal to make it work. It's like you prepare all this time and then you're on. So that was really, really exciting.
Thank you so much for being here. I was just wondering, are there any problems with neutrinos coming from the sun kind of drowning out potential detections from the black holes and other interesting things that we saw, or is that not a problem?
Well, neutrinos were initially 25 years ago when we started this. We wanted to see neutrinos from the sun and study them, and we used them to discover neutrino oscillations. Now, 25 years later, we're building experiments that are so sensitive and that are looking for dark matter, where the neutrinos actually are becoming a background. This is the progress that the field has made. Initially, we were really counting individual neutrinos. The SNO experiment, the Sudbury Neutrino Observatory, had on average about 15 to 20 solar neutrinos a day. So you could really count them, identify them, and then over years you got enough data to actually make measurement. By now our experiments are so sensitive that we are talking about the neutrino fog, and we are trying to find dark matter interactions in the neutrino fog. So the detectors that we are using to detect neutrinos or dark matter are all very sensitive to very faint interactions, and these interactions can cause glitches of light that we are trying to see. And so distinguishing those is difficult, whether it's a neutrino or a dark matter particle. So what was the signal 20 years ago is now our background, and we're just trying to go beyond that.
Thank you. Maybe this will follow up from that. In the Canadian section at the beginning of the film, they mentioned neutrinos. They use the expression a mirror image. Do you recall that? I didn't know what would constitute a mirror image of the neutrino.
I didn't quite catch that phrase, but what the original SNO experiment looked at neutrinos from the sun. We know that the nuclear reactions in the sun produce neutrinos. They're streaming down on us, and we used the SNO experiment to essentially count and look at the type of neutrinos coming from the sun, and we used that to establish that neutrinos are changing flavors, that they can oscillate between different flavors. Currently, the follow-up experiment, the SNO Plus experiment, is looking for a rare nuclear decay that has never been observed, which would demonstrate that neutrinos are their own antiparticles. So that is now the big question in neutrino physics. Are neutrinos their own antiparticles? We know there's antimatter, But neutrinos have properties like no charge that allows them to potentially be their own antiparticles. And if we can prove this, that would give us a pathway to understand the creation of matter and why we live in a universe filled with matter. So maybe that's where the mirror image came from, but I missed that particular.
Thank you. I have one more follow-up. For South Pole, when they drill the holes through hot water, do they then extract the water and then study the water?
So we did take a little bit of the water, but the water gets recirculated in this water jet, so it's it gets quite dirty. So the water remains. Most of the water remains in the hole. Otherwise, the hole actually collapses on itself. There's so much, pressure from.
Is that a missed opportunity? Could we have discovered something?
So a few years later, so you can do ice core projects. So those are separate projects. So a few years later, they drilled ice cores. To extract
At that same depth.
yeah. There's so I think China went all the way through to the lake that is underneath, and so you could also get at the water that is 400,000 years old.
I think the film said one of the big questions was like, as you said, why do we live among matter, and why is it dark matter instead of nothing, and questions like that. And I was wondering, kind of like a two-parter, like how would the neutrino observatories answer that question, and also like what are the stakes of that question? If we had a conclusion, what could that lead us to in the future?
Yeah. So IceCube can look at dark matter, in that. Dark matter can accumulate. If they can interact with protons, for example. So they can accumulate in the core of the sun, and then the dark matter might interact with each other and then annihilate and produce neutrinos, particles that we'd be able to see. So IceCube does try to look for these excess in the number of neutrinos coming from the sun to try to see dark matter. The implication of that is, so we know, we can see effect of dark matter through gravity, through the motion of stars and so on. We don't know what it is, and so if we do see this excess of neutrinos coming from the sun, then it would tell us a little bit about how they might interact with protons, for example.
Yeah, just to perhaps expand on this a little bit, the question of what is dark matter and what role do neutrinos play in the evolution of the universe really go back to some of the biggest and deepest questions that we have about where we come from. On the side of dark matter, we think we have a picture of cosmology, but the truth is we only understand 5% of the universe. The rest, we have no idea what it is. We call it dark matter and dark energy, a force that drives the universe apart and something that fills the universe, but we don't know what it is. So there is a clear gap in our understanding. And then there's also the question of how did we end up in a world that's made up of galaxies, matter, after the Big Bang, where we had, we think, an explosion, an energetic event that produced particles and antiparticles. They annihilated, but we are left with matter. And as far as we can tell, there's no appreciable amount of antimatter in the universe. There are no antimatter galaxies. And so we want to understand, where did this come from? And it turns out that neutrinos may actually hold the clue to this. They were created early in the universe. If they are their own antiparticles, they might provide us a pathway to explaining this imbalance. And so the question of dark matter and neutrinos is really central to understanding what happened in our universe.
Hi, thank you so much. I have a question about, so there's these three places, and I'm just wondering what are the differences between the three places? Like, are they built for different capabilities or specializations or something like that?
Yeah, there are three very different places. So I started out as a graduate student in Canada at the Sudbury Neutrino Observatory. At the time, and it still is, an active nickel mine. So it was built as a nickel mine. The nickel came from the meteoric event that you heard about. And so we just used the mine as a way to get deep underground, to get away from cosmic rays and all the disturbing radiation. And so we had to go underground with a bunch of miners. I still have my training certificate from being an Ontario miner, so I had to do a week-long training to be able to go underground. And then we built this laboratory there. Now it's a big facility with multiple experiments. Kamioka in Japan was also a mine, much older. It's now no longer functional and has been turned into a scientific laboratory with multiple experiments. And there you can drive into the mountain. It is much easier going in, taking a truck, driving into the mountain than actually taking the cage underground and walking a mile to get to your experiment. And then, of course, South Pole, and Reina should talk about this, very different place, and the US has a unique position there because it operates the station, the scientific station, exactly at the South Pole. And that gives it access to one of the most unique locations on Earth where you can do observations of neutrinos and also cosmic microwave background that you can't do anywhere else.
Yeah, and get into the South Pole. We only access the top of the ice, and most of the shielding from cosmic rays and so on is coming from the ice that we drill a hole into. So to get to the pole, you have to go to Christchurch, New Zealand, and then you take another flight to edge of Antarctica, another flight. So it's a very different experience. And you're supposed to get to the most remote place on Earth, and then you have all your colleagues there to work with. So it's a very different kind of experience. The tunnel you saw in the film at the South Pole is actually a sewer access tunnel that people decided to put shrines into. And then we're wiser now. We're a little bit older now. So that was 2010, right? And you were there earlier to Canada and Japan. So we're a little bit wiser. So the lab that we work at now is in Italy. And it is also a horizontal access. It's actually a highway tunnel, so it's very comfortable. You just drive on a van or whatever regular car, Fiat. Fiat Cinquecento, so you can have your cup of coffee, cappuccino in the morning. You drive in, you do your work, you come out and have your gigantic lunch, and then have espresso, and then go back in. So that's a very comfortable laboratory, and that's fun, don't you think? Yeah.
Yes, and very different from snow, where you took the cage underground in the morning at 6 a.m. and you were underground for 12 hours, and you had your lunch underground. And in the Canadian winter, you would come up and you would not see the sun all day long. So.
Thank you so much. As a graduate student, I'm wondering how you feel when you work in such remote or isolated places for such a long time, and you just do technical things every day for a long time rather than those artistic things we see in the movie. So I feel like very different. How do researchers keep motivated by those big scientific goals or
Yeah, that's a very good question, but I would like to emphasize also what Reina alluded to earlier. What I found amazingly inspiring was the teamwork. So all of these experiments are really teamwork. You're not working alone. You're working with a group of people, other students, technicians, postdocs, and seeing what you can accomplish together when you all have the same mission and vision is actually quite inspiring. And it is a truly unique experience. I mean, you realize that not many people have a chance to experience this and do this. And this is something that struck me when I was sitting here and watching this on the big screen. Having had a chance to work at all of these three places, it's been a really truly unique experience, and I value this. I have to admit there were moments that were, as a graduate student, dark and long, and I remember trying to get the snow detector up and running, and we had all sorts of problems. Now we don't talk about it anymore, but there were many nights when we thought I would never get my thesis, and the postdocs were desperate, but then you really work together as a team, and I credit our leadership, our senior leaders who actually kept us going and kept us focused and conveyed the optimism. Yes, we do get this running, and in the end it turned out to be okay. So
I think the experience at the South Pole was a little bit different than the other labs, and also in Italy. Everybody's staying at the South Pole station, and so we're living together. There's a cafeteria. They allow for 3,000 calories per person because you spend a lot of energy being outside. So you eat together. You're sleeping. You do get your single room, but the walls are paper thin, and you can hear it. So you're just kind of on top of each other. The showers you're supposed to take, not take more than 2 minutes. I think twice a week. They've increased it because now they have a better supply of water since when I was there. But you have also other experiments there, and you saw a glimpse into the life of people who go there. So there's like a music room, there's a gym there, there's the sewing room that you saw. So there's like in greenhouse. So there are like a little bit of a diversion that you can do, although. When you're there, short term, like I was for 2-3 weeks, you're really focused on getting things done and doing that. But what I want to say is, you also see how different collaborations work. So in addition to IceCube, there are other scientific experiments there. So astrophysics-wise, there's BICEP, which is looking for cosmic microwave background. There's South Pole Telescope, IceCube, so those are the three astrophysics groups, and then there's also people who are studying neutrons. The balloon launch that you saw is a weather mapping, so there are people doing that kind of stuff. And there's pub trivia nights, and you can see actually the different characteristics of all of these collaborations. So IceCube, for whatever reason, we're just a bunch of cowboys. So we have ice drillers. We just have this very much of a little bit more of a cavalier attitude than the South Pole Telescope or the BICEP folks. So the kinds of questions that we could answer are very different from the kinds of questions we could answer. So that was fun. There's, once you get to the edge of Antarctica, you also get penguin scientists and wildlife, glacier, people who are studying glaciers. People were studying landscape of Antarctica to compare it to landscape in Mars. So you get to meet all sorts of really interesting people. So it's never boring.
I think we have time for one more question.
I think it's really interesting. Hi. Thank you so much. I really enjoyed it. I think it's really interesting to hear that the South Pole has data that stays over the winter, and then they eventually carry it off by hand. Is there a reason why they don't email it off, or that it's not accessible? I know investigators who are much more eager to get data than that, but I also understand, I like the way that it referenced the time scale of neutrinos and how long that they've been traveling compared to this ice cap that's like a blink of an eye. So maybe there's no rush. But it also, beyond thinking about getting the data and why it's so slow, I was just wondering if you could comment on when you are looking at data. I have no idea what it looks like. If you could just give me any kind of reference to someone who is not in this field, what you're looking at, maybe what the scales are measured in, and just quickly, if you could say what are the kinds of differences in the data that you might get from one of these places, the snow in Canada, to the South Pole. Are you getting the same kind of data? Are they different data? Are they all able to look at different phase oscillations of neutrinos?
Okay.
Thank you.
Yeah. All right. So what does data look like? So data is basically the time stamp of one of these detectors seeing light. So you have a bunch of different detectors, and then as the particle goes through the medium, they emit light. And so if a detector here saw light
from where it is or where it thinks it came from.
So you have the particle. So neutrino comes in, it interacts with the water, and then it turns into electrons or muons or some sort of charged particle. And as that charged particle goes through the ice, that they can emit what's called Cherenkov light, and then that light can then be detected. And so by reconstructing when and where the photon hit a detector, we can pinpoint back to where that neutrino might have come from. And then you can also see how much light there was. So that's the information that we have. In IceCube, we transfer about 10% of the data via satellite. So that's as much data as we can send through satellite. And actually, when I was there, you only had internet access for 8 hours, a few hours in a day. I think it was 8 hours. And the rest of the time, black. Yeah, nothing. No social media, nothing. So that's why we don't have enough bandwidth to take all of the data out. But so we send with that 10% of the data, we do what's called triggering. So we tell the experiment we want to quickly send an event that looks like this to our computers in Wisconsin, and the rest we keep on tape. And so if there was an event like supernova or some star exploding somewhere, then we could take that data, and we actually send out alerts to other telescopes and say, hey, we saw something. Do you see anything?
Yeah, and just to, since you asked about both locations, basically at SNOW, we also use the light from the neutrino interactions to detect that an event happened, and then we use the directional information to point back to the sun. So basically, we looked at neutrinos from the sun. IceCube experiment is looking at cosmic neutrinos, so we can pinpoint the directions. The amount of light and the type of interactions give us different energies, so they're different energies of the event. There was one thing, I don't know if people caught it in the movie, for the SNOW experiment, it showed a little loudspeaker sitting next to the monitor, and you might ask, so why is there a little loudspeaker sitting there? Because you have all these computer displays and fancy monitors. And actually, it started when we commissioned the SNOW experiment. So you have the background events essentially is a constant rate. And so it's like white noise in your experiment. And when we commissioned the SNOW experiment, we had occasionally flashing PMTs that would spontaneously break down and emit light. And the quickest way to actually identify them was to listen to the loudspeaker. If suddenly you had a burst of noise in the loudspeaker, and you knew that one of your PMTs was going crazy and you better shut off that high voltage. And that was much faster than waiting for or looking at the event display. And especially if you're on midnight shift, you just listen to the loudspeaker and you know that your experiment is going well.
Well, thank you very much. We have to leave now because there's another event after us, but thank you.